our discussion on the behavior of 2 degree of freedom system, and then there we developed the equation from the governing differential equations from the considerations of the free body diagrams, and then uh, for finding out the natural frequencies and mode shapes, which are the primary dynamic features of a system. We considered the free vibration equation. That means the force vectors we considered as a null vector, and then also we got rid of the damping, and then ultimately while considering modal vibration, that means vibration which is taking place in a particular mode, we discussed the fact that the shape remain constant, but the amplitude may change depending on the initial conditions or depending on the loading functions, whatever it is. And then that's why uh, the shape is given by a vector. So, and on the other hand, the time variation is given by a common function. That means if there is a common function, here we have written that the solution will be of the form x1t equal to u1 ft, x2t equal to u2 ft. That means whatever be the value of ft is there, the ratio of the displacement of these 2 degrees of freedom always remain u1 is to u2. So that means the shape remains same, but if the ft becomes, and ft will also be same for both the equations, but ft itself become different, and it may take different value at different time, but and that will change the displacement of the whole system. But in the process, the x1t is to x2t, this ratio will remain same as u1 is to ut, and this we are calling as a modal vibration. When a particular mode is maintained, then the system is bound to vibrate in a particular frequency, which we call the natural frequency. The lowest natural frequency is called the fundamental natural frequency, and the corresponding time period, that means 2 pi by, if the lowest natural frequency is omega 1, then 2 pi by omega 1 is equal to the highest natural period. And this mode, normally the lower modes, they participate more in this kind of vibration, because all of you know, I mean, in any general situation of the vibration, uh, all the modes participate in general, but the extent of the participation becomes different, and always the maximum participation become that of the first mode, and then the second mode, then third mode, and so on. Because to excite the participation in the first mode, the energy required becomes least. And as I have told you, that most of the phenomenon of the mechanics in this universe can be explained in terms of the energy principle. That means the fact that any system wanna go to the as lower potential energy as possible with respect to its immediate neighborhood. That means I'm telling with respect to its immediate neighborhood, because if I take a ball here and then if I try to place it somewhere, then its location cannot be considered with say some body which is at the bottom of the river Ganga, because this is not the immediate neighborhood. So from this ball to go there, at the bottom of the Ganga, it will have least potential perhaps, but it will not be in a position to go there. So with respect to the immediate neighborhood, we considered that it will, if I give it a perturbation, it will try to move, and then in the process it will try to be stable in a position which is having minimum potential energy with respect to the immediate neighborhood. And then as we discussed last time, that if ft is real, then a1 a2 and will be, if a1 and a2 are complex conjugate, then the function will be the displacement function will be real, and we may then consider a1 a2 and equal to c cos phi, and here it should be I a1 a2. So this I a1 a2 can be expressed as c sin phi. So then it becomes a function of cos terms, two cos terms, as well as the summation or subtraction of two sine terms, and so we can express them in a more compact form, constant c into cos omega t minus phi, and then what will that c can see what is c? C is nothing but, if we add up square this and add up these two equations, then c square cos square phi plus c square sin square phi will be equal to a1 plus a2 whole square plus I square into a1 minus a2 whole square. So that means c will be square root of a1 plus a2 whole square minus a1 minus a2 whole square. So that's how we can find out c. It will be the square root of these terms, the square root of the summation of the squares of this term. And then, you know, if we substitute x1 t equal to u1 ft and x2 t equal to u2 ft, then x1 double dot t will be u1 f double dot t and x2 t will be u2 f double dot t. And then if I substitute in this equation, instead of x double dot t and x1 double dot t and x2 double dot t, so we will get this form k11 minus omega square m1 into u1 plus k12 into u2 plus k12 u1 plus k22 minus omega square m2 into u2. That means, and then on the right hand side, it is a the right hand side terms are 0. That means if we write it in the matrix form, then here we will have a, on the right hand side we will have a null vector, and then as I told you that this is the form of an eigenvalue problem. That means the stiffness terms minus some lambda, and again here the I mean in the diagonal stiffness term minus some lambda, and here also the stiffness term minus same lambda. So this lambda is actually called the eigenvalue, and this kind of problem is called the eigenvalue problem. So we know that any set of simultaneous equation may have three types of solution. One is a unique solution, one is infinitely many solution, and another is no solution. So since it is a vibration problem, we want real and at the same time non-zero or non-trivial solution. So if we go for a unique solution, then since both these are 0, therefore u1 and u2 both will be 0. So that will denote the static condition. Therefore we are discarding that solution, and then we are putting the condition of the infinitely many solution. So if we use Cramer's rule, can you tell me what will be the condition for infinitely many solution? What will be the condition of infinitely many solution? Cramer's rule equal to Cramer's rule gives us, say in x, y, z, it will give us d1 by d, then d2 by d, and then d3 by d, where d1 is nothing but in the first row, the vector at the right hand side, that means this vector consisting these elements are substituted. In the second case, in the second column, I mean this right hand side vector is substituted, and in the third column this right hand side vector is substituted. So if there is a column in any matrix which are having all zero, then the matrix will have its determinant zero. So if all this, I mean, if all d1, d2, d3, all these determinants become zero, then the only way to have infinitely many solutions is that d should also be zero. That means determinant of this matrix should also be zero. Then it will have a 0 by 0 form. That means it will have infinitely many solutions. How? You just considered it in terms of a single variable, that if we can write the equation in the form that 0 into x equal to 0, then whatever value of x we take, say 1, 2, 3, 4, 5, 5.5, 3.75, so 0 into that will be equal to 0. So the equation is being satisfied by infinitely many values. So that's how we can show that if there are more than one variables, then also we can get the infinitely many solution. But only thing is that within this infinitely many solution, there will be proportionality. That proportionality will be maintained. So this solution will be nothing, these solutions are called eigenvectors, and they will be nothing but the mode shapes in this particular, in the vibration problem, mode shapes in these guys. So we put the condition that determinant of this matrix with omega square, I mean, that is equal to 0. So this is called characteristic determinant, or the whole equation is called characteristic equations, and then we get it like this: m1 into omega to the power 4 minus this whole term into omega square plus some constant terms like this. Now this is called characteristic equations, and from this characteristic equation we get this kind of a solution. There are two possible solutions. So and corresponding to each value of omega, that is omega 1 and omega 2, we will have one vector which will be the mode shape vector. So the two terms of the first mode shape vector we are calling as u1 to the power 1 and u2 to the power 1, then u1 2, u2 2, that is corresponding to omega 2, and then we are having the ratio. That means, you see here there are only 2 degrees of freedom, which indicates that means the ratio of the two displacement will remain constant, and then only a particular shape will be maintained. So actually we can use any one of the equation to get them. If we use the first equation, that means here if we get the first equation k11 minus omega square m1 into u1 plus k2 into u2, if I use this first equation, then I will get a ratio like this, and then if I get the second equation, we'll get the ratio like this. That means for infinitely many solutions, if we have n number of simultaneous equations, actually out of them n minus 1 number of simultaneous equation will be independent equation, and the last equation, they can be expressed in terms of the other n minus 1 equations, and therefore so that equation is invalid, and we have to work with n minus 1 equations for solving for n variable, and therefore what we will do that n minus 1 number of variable we will try to express in terms of one particular variable, and then for each value of the that particular variable, we'll have a set of values for n minus 1 number of variables, and we can choose any value of that particular variable. So we can have infinite number of solutions where the shape will remain same. Shape means the ratio of the elements of that vectors will always remain same. That means the proportionality between them will remain same. And then this is called, mathematically is called eigenvector. But for the vibration problem, this will be called as mode shape, because if the system vibrate with the frequency omega 1, then it must maintain the first mode shape. They are they are together, so they cannot be separated. Similarly, if the system vibrate with the frequency omega 2, then it will automatically maintain the second mode shape. Or other way speaking, you maintain the second mode shape in the at the initial position, and then you release it, so it will keep on vibrating, maintaining the same shape, and the frequency will automatically be omega 2. So from any one of that means two equations we do not require for two variables. We require one equation for two variables, because one variable will be expressed in terms of the other, and then that is why u superscript 1. So that will be that can be written as u1 superscript 1, u2 superscript 1, and we can write it like 1 u1 1 and then 1 r1. That means one variable. You know that for matrix or vector, if we take anything common, then its basic characteristics doesn't change. Therefore we can say that the mode shape is 1 r1. Similarly, in the second case, we can say the mode shape is 1 r2. Is this understandable to everybody? Any question on this? Hello? Hello, my friends. This is a very, very conceptual zone, so that's why I'm trying to harp upon this. Once you understand this, then multi-degree of in the multi-degree of freedom also the same philosophy will be followed, and it will be easier for you to grasp. So if we write down the first mode shape vector x superscript 1t, then it can be written as u1 into 1 r1 cos omega 1t minus phi1. Similarly, x2t, that can be written as c2 into 1 r2 then cos omega 2 minus phi2. And naturally, the general, since each of the solution satisfies the differential equation, so the summation of them will also, that is, if each of the solution we substitute in the left hand side, then the right hand side will become 0. So if we substitute summation of them, then also the right hand side will be 0. So from the viewpoint of the differential equation, this will be the most generic solution, that the summation of all these displacement in the shape of mode shape. So now you take up a problem. Say initially our problem was, you see, m1 and m2 0 0, k1 plus k2 minus k2 k2 plus k3 x1 x2 equal to 0 0. So this was the free undamped free vibration equations for the system. Then now if you consider m1 equal to m and m2 equal to 2m, that means you please write down the mass matrix, that it will be m0 0 2m. Can you please write it down? m1 equal to m, m2 equal to 2m, k1 and k2 is given as k, and k3 given as 2k. So if you come here, in here, you see m1 equal to m, m2 equal to 2m, and then k1 equal to k, k2 equal to, let me just check, k2 equal to k, and k1 also equal to k, and then k3 equal to 2k. So by seeing this system, can you write down the equation in this form? In this form, can you write down here? You can just substitute the values and you can get the equations. That means we will have m 0, 0, 2m. Then here we will have k1 plus k2 means 2k. Then minus k2 means minus k, and k2 plus k3 means k plus 2k, so 3k. So this will be our steepness matrix. So with this, can you now just try to find out the mode shape the way I have discussed? Okay, so then our next attempt will be to find out the characteristic equation. That means characteristic equation means in terms of omega. Since it is a 2 by 2 matrix, so we will have it in terms of omega square, the square of omega square, or omega square we can denote by lambda. So we will have a quadratic equation in terms of lambda. So you know how a quadratic equation will be. Can you write that equation in terms of the lambda for this particular problem? Just you look at this form, this may help you. You see, look at this form. This may help you. Then you will take the, you will find out the determinant of this matrix. Determinant of this matrix will be equal to 0. That was the consideration, isn't it? That was the consideration we made here. So that was giving us the characteristic equation. Instead of omega square, you may substitute lambda for convenience of your calculation or dealing with the equations. Just in this equation, you substitute what is k11. K11 is k. Then m1 is m. K12 equal to minus k. Then k22 equal to k. Plus with this k3 was there. So that is also 2k. So it will be 3k minus omega square into 2 or lambda into 2m. Couldn't equal omega. Okay, so these are the two values are coming. So omega 1 will be square root of these values. Okay, because lambda equal to omega square. So this will be omega 1, this will be omega 2. Why we will call it omega 1? Because this is the lower one and this is the higher one. So now can you try to find out the mode shape of your own? So next day you are also seeing the calculation. So next day at least you come with finding out the mode shape, and then we'll discuss further.